Good morning students. In today's class we will discuss what are the different types of oscillators and we will see operation of each oscillator in detail. Okay, firstly, so oscillators are classified into many types, but in our syllabus we have two different types of oscillators are there. They are LC oscillators and RC phase shift oscillator. Up to that only we have in our syllabus. Okay, now first we will see LC tuned oscillators. Okay, first one is the LC tuned oscillators. Next one is the RC phase shift oscillators. Now, so this is a circuit diagram of the Hartley oscillator. Okay, under LC tuned oscillators we have two different types of oscillators. One is the Hartley oscillator. Second one is the Colpitt's oscillator. Okay, two different types of oscillators are there under LC tuned oscillators. L means inductor, C is the capacitor, which means in the feedback network we will use a L and C components. That is why they are called LC oscillators, LC tuned oscillators. Okay, I hope you are clear, right? So L is the inductor and C is the capacitor. Okay, C is capacitor, which means we will use inductor and capacitor in this circuit, in this oscillator. Okay, that is why they are called LC tuned oscillators. Tuning means they are tuned to a particular frequency. Both these L and C components are tuned. Tuned means they are synchronized to a particular frequency value. That is why they are called LC tuned oscillators. Okay, because we are using the inductor and capacitor in this oscillator, the name comes LC oscillator. And if you come to the specifications, specifically it is a Hartley oscillator. So now we will see the construction and operation of this Hartley oscillator. Okay, now we have a bipolar junction transistor. This is a bipolar junction transistor, BJT, and we know that in transistor we will have three important terminals. Transistor has three terminals. One is the base, B for base, C for collector, E for emitter. Okay, E is emitter. Now this arrow indicates the conventional current direction, and here R1 and R2 are the biasing resistors. So these biasing resistors are useful in order to keep the operating point in the region, active region. Okay, to keep the operating point in the active region, we will use this R1 and R2. These are the biasing resistors. Now see this RE. So because this resistor is connected to the emitter, we got the RE emitter resistor, and this is a capacitor, emitter capacitor. And this is generally this capacitor is to take the output, or otherwise in order to block the DC. Now, so this is this part up to this is the transistor amplifier. In the just previous class we have seen. So what is the block diagram of an oscillator? What are the different blocks of the oscillator block diagram? We have a transistor amplifier, then feedback circuit, then oscillating circuit. So therefore this is the transistor amplifier. From here to, so this entire part, this part is the transistor amplifier, and so this is the feedback. See, so we are taking the output and we are combining it to the input. So that is feedback circuit, and this is what is the oscillating circuit. Okay, this L and C, L inductor L, and this capacitor. So the capacitor with this arrow, it is called a variable capacitor. It indicates a variable capacitor. So we can change the capacitor value. Okay, now see, we are applying the input to the base. See, we are applying input to the base, and we are taking the output across the collector. Okay, we are applying input at the base, and we are taking output across the collector. Now here you will get the sinusoidal oscillations like this. These are the oscillations you get here at the output of the oscillator. Now this is the construction, right? We will take a C amplifier. See, we are taking output across the collector, and apply input across the base at the base. So what is the common terminal? Emitter. That is why it is called a CE amplifier. And for this CE amplifier, we apply the input across the base and take the output across the collector. And this is the tuned circuit. Okay, this circuit, this L and C combination circuit, it is called tuned circuit. Okay, tuned, T-U-N-E-D, tuned LC circuit. Okay, this is a major important block in this oscillator, tuned LC circuit. Now we will see the operation of this Hartley oscillator. Now, and also another thing, so this VCC is the supply voltage which is used to operate this transistor or oscillator. Okay, without, see, because supply voltage must be given to the transistor to operate the transistor in the means required mode. Now, so what happens is whenever, so coming to the operation of the Hartley oscillator, whenever the switch is closed, then what happens is, so this capacitor charges to the maximum value. Whenever switch is closed, this capacitor charges to the maximum value. Then whenever, so once capacitor charges to the maximum value, then that capacitor discharges to the inductor. So in this way, okay. Suppose see, so initially what happens when switch is closed? Switch closed means, you see this arrow, just switch is closed in this direction. Now current flows like this, and current flows through this capacitor, it charges to the maximum value, and once it reaches to the maximum value, then what happens is it discharges through this path and it is connected to the emitter. You see, emitter is so that we'll take the, here the, it is a transformer is center tap, and we take the signal at the middle of the, so this inductor coil, so then it is given to the emitter. And also another terminal is connected to the base. We take the out, so we give it to the emitter, and also we give it to the base. Okay, see this. So PQR, this R terminal is connected to the base, and P terminal is connected to the collector. Collector means at this terminal we take the output, and here we apply the, so see this, we are applying the input. So therefore output is again connected to the input. This is called a feedback connection or feedback block, and then we are taking the center tapping. So therefore, like that, what happens whenever you switch is closed, capacitor charges to the maximum value, and after reaching the maximum value, capacitor discharges to the through the inductor, and like that, what happens, you get oscillations. So therefore, once capacitor charges to the maximum value, during charging and discharging, it will generate oscillations. Those oscillations are given to the base, and the C amplifier amplifies that oscillations. And also another important point is, so we know that Barkhasan criteria, in the Barkhasan criteria, the phase shift of the output signal, it has to satisfy the loop gain must be 0 degrees or 360 degrees. We know that the C amplifier provides 180 degrees phase shift. This is because it is C amplifier. So between if you compare the base at base, the polarity, and also polarity at the collector, if you compare the waveform polarity at the base and collector, they are differed by 180 degrees phase difference, and also another 180 degrees phase difference is provided by this L and C elements. So therefore total 360 degrees phase shift will be there, which is the output which is produced as the output of the collector. So therefore Barkhasan criteria, however the loop gain, magnitude of the loop gain is always greater than or equal to 1 practically, and also phase shift is 360 degrees. 180 degrees phase shift is provided by this BJT, means C amplifier. Another 180 degrees phase shift is provided by this L and C elements. So therefore finally here you will get a 0 degrees or 360 degrees phase shifted signal. 0 or 360 means there is no phase shift at all. Like that you will get a oscillations here. But here one other point to remember is, see this capacitor here also one capacitor is there. These capacitors are used to block the DC which is entering into the amplifier. If you want to block that, because see it has to amplify this amplifier is designed to amplify only AC signal. If any DC signal tries to enter into this amplifier that is blocked by blocking capacitor connected in base, and also to avoid means to block the DC in the output we'll use this one, otherwise coupling capacitor we can say that. So therefore here, so this LC circuit is a responsible circuit for sustained oscillations in the output of the oscillator. So now this, by changing this C value, we can change the frequency of oscillations. Suppose if you want to find out what is the frequency of oscillations in the output of the circuit, then this is the formula for that. Okay, this F is nothing but F is the frequency of oscillations, that is the 1 by 2 pi under root LT. LT means L equivalent or L total inductance. The total inductance is equal to, so we say that L1 plus L2. So this, because we are taking center tapping here, so that is considered as a, so L1 plus L2 plus 2M. Okay, where M is the mutual inductance, so that you can get from the values. I mean, so you will be given, otherwise you have to calculate based on some coupling coefficient and all. Okay, so therefore mu is the mutual inductance, M is the mutual inductance, L1 and L2 are the, so these are the inductors or inductance values which is present in the LC circuit, and you can calculate so this frequency of oscillations for this circuit. Now what is LT means? LT is the equivalent total inductance value, and suppose see, I want to, for a particular value of LT and C, I will get, suppose you assume that I got some 5 kilohertz signal. Okay, frequency is measured in the kilohertz. So if I want to change the design, I want to get a 10 kilohertz signal, then so this C value can change it, because it is a variable capacitor. By varying the C value, you can change the frequency of oscillations. That is about the Hartley oscillator, because it is called Hartley oscillator, and also we are taking the center tapping point, means inductor is center tap. And we consider, so this is a L1 and L2. So you can change these points. You can change the center tapping point. So at the bottom side, or also you can keep it at the center. So based on the location of the center tapping, so you will get voltage. That voltage may be given here, or emitter or base, that will change. Okay, so that is the purpose of the center tapping inductor or center tapping inductor coil. And so this tuned circuit is responsible for only these oscillations. However, the amplifier amplifies that oscillations, and another one is feedback. So output and input are connected. That is why, so 3 blocks are covered here. So in the basic oscillator we will have a transistor amplifier, feedback block or feedback element, and another element is oscillating circuit. Okay, this is the oscillating circuit. Okay, and this is Hartley oscillator. Coming to the advantages of Hartley oscillator, you see the main advantage of this Hartley oscillator is it will generate the wide frequency range of oscillations. So it can generate a wide frequency range of oscillations by varying the capacitor value C. Right? Different values, by changing the value of capacitor, we can get a different frequencies at the output, so that it can cover a wide range of oscillations or constant oscillations. Now another important advantage is, so it will have constant amplitude oscillations. Sustained oscillations means 2 things it has to satisfy. One is the amplitude must be constant, and also frequency must be constant. Amplitude and frequency must be constant. Whenever these two are constant, we say that it is a sustained oscillation. So amplitude constant means the amplitude of the generated or output of the oscillator must be constant for all the time. Okay, then only we say that it is sustained oscillations at the output of the oscillator. So these two are provided by the Hartley oscillator. Okay, now another variation is Colpitts oscillator. Okay, another type of LC tuned oscillator is Colpitts oscillator. Only the difference between Hartley oscillator and Colpitts oscillator is, so we take this at the midpoint of the these two capacitors, we give it to the emitter. Previously, we are center tapping the inductor coil. Here, what we are doing is, we are connecting these two, actually these two capacitors are here, and at the middle of these two capacitors, we take a signal, and the signal is connected to the emitter of the transistor. That is the only difference. And because of this, what happened, and another difference is there, that is a radio frequency coil. We use a radio frequency coil. RFC means radio frequency coil. Again, it is an inductor only. It provides a open circuit, electrically open circuit, not physically. Electrical open circuit means it provides infinite impedance. So whenever signal comes to this point, so it provides an open circuit at resonant frequency. Whenever this tuned circuit is in resonance, then it becomes open circuit and also it provides a low resistance. So therefore, maximum you will get a maximum signal in sustained oscillations at the output of the Colpitt's oscillator. Remaining operation is same. See, this is the amplifier. See, and here also it is a C amplifier only. See, we are applying input to the base. We are taking output across the collector. So that is why we say that it is a common emitter configuration, and it is a LC tuned circuit. So here we are taking this center tapping value in the middle of these two capacitors. So because of that, then what happens is they are in the series connection. Current is not at all divided there. So that is why when two capacitors are connected in series, they will take equivalent total capacitance C1 C2 into divided by C1 plus C2, and also L1. This is L1. So here now see, we will see the coming to the operation. However, this is a blocking capacitor. This is also coupling or blocking capacitor. Now whenever switch is closed, then current passes through this coil. See, this connection is there. Whenever here current passes this, and here what happens is, then so whenever current passes through the capacitor, it charges to the maximum value, maximum capacity of its capacitor values, and then whenever these capacitors are fully charged, then it discharges to the inductor. Okay, so whenever this charging and discharging creates the oscillations. Now these oscillations are given to the base of the C amplifier, that is like input. Whenever oscillations are given at the input of the amplifier, it amplifies the signal. So therefore you will get the oscillations here, constant sustained oscillations you will get at the output of the transistor, that is at the collector. So remaining operation is same, right? So charging and discharging takes place, and the only difference is we take the center tapping, or otherwise we can say that, so this point at the midpoint of these two capacitors are actually they are taken the signal, and that signal is given to the emitter of the transistor. Okay, like this, ground, simply you can say that it is a ground. Now here we can calculate the frequency of oscillations, that is F is equal to 1 by under root L CT, where CT is the equivalent capacitance or total capacitance of that. So whenever now, so actually these two capacitors are in series, that is why when capacitors are connected in series, C1 C2 by C1 plus C2 is the equivalent of total capacitance. So here that CT comes here. Okay, like that we can generate sustained oscillations in the Colpitt's oscillator. Okay, so these are the two types of LC tuned oscillators in our syllabus. Okay, now we will see another type of oscillator. Just now we have seen what are the LC tuned oscillators. Now we will see RC oscillator. Okay, RC oscillator, R for resistor, C is the capacitor. Okay, using these R and C elements in the feedback network, we design the oscillator. That is why we say that they are RC oscillators. RC oscillators, and specifically the name is RC phase shift oscillator. Okay, in this oscillator we will use the R resistor and capacitor elements in the feedback network. That is why the name RC phase shift oscillator. And so now you can see here, this is the RC phase shift network. Okay, so 3 capacitors, 3 resistors connected in order to provide a 180 degrees phase shift, because we know that, however, you see, we apply the input to the base and we take the output at the collector. Okay, this is a blocking capacitor, however, the coupling capacitor. Now this is what happens is we take the output across the collector, we apply the input across at the base. Now we say again it is a CE amplifier. Okay, this only this portion from here to here, it is a CE amplifier. Then the CE amplifier, in the CE amplifier, the phase difference between the input and output of the amplifier is 180 degrees phase difference. So the signal which is present here and the signal present at the collector with respect to the signal present at the base, they are out of 180 degrees phase difference. And here you see this feedback network also provides, so here 60 degrees, 120 and 180. So this 180 and amplifier provides another 180 degrees, total 360 degrees. So therefore magnitude, so according to the Barkhasan criteria, magnitude of the loop gain must be 1 or greater than, slightly greater than 1, and phase difference must be loop phase angle of the loop gain must be 0 or 360 degrees. Okay, now that 180 degrees is provided by the RC phase shift network, another 180 degrees is provided by the, so this C amplifier. However, this C, RE, they are common. So this is a emitter resistor, this RL is the load resistor where we take the output. Okay, and this is a blocking capacitor, and this is a CE emitter capacitor or bypass capacitor. Okay, now see, this is a feedback network, and we take the, see here, this is the output, and this output is connected to the again input. Okay, that is why we say that it is a feedback connection. You see, feedback means what? We take the part of the output signal, we give it to the input. Now you see the output signal is, we are taking here output signal, and that output signal is given to the base of the C amplifier. So therefore output is connected to the input, that is why we call it as a feedback. And this is a RC phase shift network. And what is the feedback? RC phase shift network, or otherwise we say that oscillating network or oscillating circuit, and this is a transistor amplifier. So these three parts collectively forms a oscillator circuit. Now we will see the operation. What happens when switch is closed? This is a VCC, right? When switch is closed, there is a power supply. Maximum you may have 12 volts like that. So when switch is closed, current passes through this, and current passes in this path. Current passes here. Then capacitor charges to its maximum value. Okay, once capacitor charges to its maximum value, then so capacitors, all the capacitor discharges through this resistors. 3 capacitors are there, and these 3 capacitors are discharges to the resistor. So this charging and discharging action initiates the oscillations in the feedback RC phase shift network or feedback network. Okay, so then what happens? Those oscillations are given as the input for the CE amplifier, and the CE amplifier amplifies those oscillations, and at the output, this is the output point where we take the output across the collector, and you will get the sustained oscillations here at the output. So this process continues. So the basic operation is when switch is closed, capacitor charges to its maximum value. Then after reaching its maximum value point, then it discharges through the resistors, and this charging and discharging action in the oscillator initiates the oscillations, and these oscillations are given to the amplifier, and amplifier amplifies those oscillations, and you will get a sustained oscillations in the output with a constant magnitude and frequency. Now, so this is the formula. This is the formula for oscillations, the frequency of oscillations. You will get some frequency of oscillations here, and these oscillations are having some frequency. That frequency is calculated by F is equal to 1 by 2 pi RC under root N. Hertz is the unit for frequency, where N is the number of RC networks. Okay, here see we can take this part as a one RC network. This is another RC. This is another RC. Okay, N is the number of RC networks. Okay, here we have a 3 RC networks. So therefore we have to substitute N is equal to 3. So you substitute R value and C value, because see, all are equivalent. R, and this is all are C only. So N is the number of RC blocks. So I told you one block, second block, third block. Like the first, second, third. So now N becomes 3. In our case, RC phase shift oscillator, N becomes 3. So based on that, you can calculate the frequency of oscillations in the RC phase shift oscillator. Now this is a comparatively LC oscillators. Construction and operation, construction of the RC phase shift oscillator is simple, and also it is having some advantages, because see, the major advantage of RC phase shift oscillator is you need not to have inductor, because inductor, whenever you use the inductor in the design, so it makes the circuit large. Okay, so circuit becomes a large circuit in the sense it occupies more area if you use the inductor. So here we need not to use inductor, and so that is a major advantage. And you see this, some more advantages are also there. It provides a good frequency stability, means whatever the oscillations they are produced at the output of the oscillator, they are stable oscillations. Frequency does not change with respect to time. Frequency does not change. A constant frequency will be there, and also amplitude also stable, constant. So therefore good frequency stability is there, and it generates low frequency oscillations. So we say that it is a audio frequency, in the range of audio frequency it generates low frequency oscillation. Below that also it will generate low frequency. And also the cost to design this RC phase shift oscillator, so it is a very less cost. That is we can say that it is a more economical. So in addition means so in spite of we will have even addition some advantages, disadvantages are also there. So the output of this RC phase shift oscillator is having a lower output, which means amplitude of the RC phase shift oscillator, the oscillations of amplitude of the oscillations and the output of the RC phase shift oscillator is having a lower value. And another disadvantage is so difficult to initiate the oscillations, because now see what happens is whenever switch is closed, current passes through that capacitor, and once capacitor charges to the maximum and it discharges to the resistor. So this charging and discharging initiates the oscillations. So this initiation of oscillations is difficult in RC phase shift oscillator, because so you don't have the facility like L here. So that is why what happens is in the RC phase shift oscillator, initiation of the oscillations becomes somewhat comparatively difficult with LC oscillators. Okay, so this is the RC phase shift oscillators. Now, so in this class what we have seen is what are the different types of oscillators, like LC tuned oscillators and RC phase shift oscillators. In the syllabus only we have these 3 oscillators only. So in the LC tuned oscillators we have a Hartley oscillator, we have seen that, and Colpitt's oscillator. Then in the RC oscillators we have a RC phase shift oscillator. So from exam point of view, so these are important. So exam like you will get questions, draw the circuit diagram of RC phase shift oscillator, explain its operation, and give the expression for frequency of oscillations. Like that you will get the questions. Okay, thank you.